In this video, we will be discussing about AFL and we will discuss about difference between CNF, which is Chomsky normal form, and another is Grebeck normal form, Grebeck normal form. So what are these two things? Chomsky normal form and Grebeck normal forms are representation for context-free grammars, right? Now let's come to the part. These two are for to represent context-free grammar, right? Now, first difference is it is represented. Chomsky normal form is represented in form of A goes to B, right? C, where A, B, C belongs to variable, right? And A goes to small a, where A belongs to terminal, right? So either on left hand side I can have one variable and on right hand side I can have two variable, or it is represented as on left hand side I can have one variable and on right hand side I can have terminal, right? Now some examples are, suppose S goes to AB, right? And A goes to B, terminal A, and B goes to AB, terminal B, right? So this is Chomsky normal form. This is also Chomsky normal form, and this is also, right. Number of steps required to generate a string of length n is 2n minus 1, right? Suppose I have A goes to AB, A goes to small a, which is terminal, and B goes to small b. So I have my A as AB and B as B, right? And A as a small a B, right? So total number of steps are here 3, right? And a string length is AB, which is 2. So 2 into 2 minus 1, which is 3. So 3 steps are there, right? Now in GNF, number of steps required to generate a string of length n is n. How? Because Grebeck normal form is representation like this: A goes to Ax, where x belongs to variable or combination of variable, and right, and a small a is right hand side terminal, right? X belongs to variable or composition of variables, right? And A belongs to terminal, right? So suppose I can have A goes to A, or X goes to A, B, C, D, E, F, something like this. These are examples. Now suppose I want to produce this AB, so I will write this as A goes to AB, right? This is my Grebeck normal form, and I can write this as, right, A goes to AB and B goes to B, so it will be AB, right? So total number of steps involved are two steps, right? Now the Chomsky normal form is used in membership algorithm, and this Grebeck normal form is used to convert context-free grammar to push down automata, right? Derivation obtained from CNF or Chomsky normal form is always a binary tree, right? Whereas here you will get a derivation, it might not be a binary tree, right? And last thing is, yes, length of production rules are limited here, not restricted, right? Now I am erasing this, and let's move on to the next topic, right? Now, how to remove null production from context-free grammar, right? How to remove null production from context-free grammar, right? So how will I do that? Suppose I have S goes to, right, a small a, capital S, A, capital A, right, where S is recognized by this capital A, which is variable, right. So I will first recognize my step 1, I will first recognize my nullable variable, right. So here A goes to epsilon. So A is my nullable variable, S is identified by it. So S is also nullable variable. So my nullable variables are A, S, right. Now I can write this as S goes to A, S, or if I put epsilon, so here I can write A, right. I will put epsilon, so I can write this as simple A, or if I write here, I put here epsilon, right. So I can write this as epsilon, right. Lambda production. So this is how I can write this as, right. I removed null production from here, right. Now suppose I have my final grammar will be S goes to A, S, A, epsilon, right. And if my epsilon is part of grammar, so I will not remove my epsilon, right. This grammar produce language A to the power n, where n is greater than equal to 0, right. If I will remove this epsilon, this will become A to the power n, where n is greater than 0, and this is not I want. So if lambda belongs to language, grammar language, then I will not remove epsilon from here, right. Now suppose I have another example, right. I have S, A, B, C, A goes to A, right, terminal A, variable A, and epsilon, B goes to B, epsilon, and C goes to C. Now S is not nullable variable as C does not go to epsilon, right. So nullable variable are only A and B, right. A and B are nullable variable, right. And I can write this as S goes to A, B, C, or I can write this as B, C. If I put terminate here A, or if I terminate B, I can write this as AC, or I can simply write it as C. If I put A and B both epsilon, right. Now A can be written as simply A like this can I write A and B. So overall epsilon is not part of this grammar, right. For this grammar epsilon is not the part, right. And I am erasing this. Now let's move on to the next topic. Next topic is removing unit productions, right. Removing unit productions. So what is this, right. Suppose I have a transition of form alpha goes to beta, where alpha, beta both are variable, right. So this is my unit production. Suppose I take an example, S goes to capital AB, and A goes to A, which is terminal, B goes to C and B, this is terminal, and C goes to D, D goes to E, E goes to A, right. Now what I can write is as B goes to C, goes to D, goes to E, right. This whole step I can write this as, right. And suppose I will rewrite this as, now E goes to A, D goes to also A, C goes to also A, B goes to A or B terminal, and A goes to A also, right? S goes to AB. So these three are unreachable. From S, if I start from a start variable, if I start going, I cannot reach my C, D and D. So I can remove this, right? For example, let's take another example. S goes to A, small a, capital A, and B. A goes to B, A, B, B. B goes to A, B, B, A. So S goes to, I can write A. Instead of B, I can write this as B, A, B, B, and B, B, A. Right. So I removed what? I removed this B from here. So by this we can remove our unit productions which are not required, right? So this is all for this video.